In this problem, we're told that an evacuated reaction vessel is filled with 0.6 atmospheres of N2 and 1.7 atmospheres of Br2. When equilibrium is established according to the reaction, there are 1.4 atmospheres of Br2 remaining in the vessel. And the question asks, what is Kp for this reaction? So when we're addressing one of these problems, our first question is always, what is the problem asking? So in this case, we see that the problem is asking, what is Kp for the reaction? Okay, so our expression for Kp based on our reaction, this is the law of mass action, is that Kp will be the partial pressure of the products, so N2, times the partial pressure, the other product, raised to its stoichiometric coefficient, so Br, the partial pressure of Br2 cubed, divided by the partial pressure at equilibrium of the reactants, so NBr3 squared. Now, we need to know the partial pressures at equilibrium in order to solve for the value of Kp. So the next question is, well, what information are we given? So we're told that our reaction vessel is filled with 0.6 atmospheres of N2 and 1.7 atmospheres of Br2. The fact that the problem statement focuses on that the reaction vessel is evacuated, that's just a clue to us that the vessel is empty otherwise, that these are the only two things that are present. Because it says that the reaction vessel is filled with these things, that implies that these are initial amounts. Initial. And then the next statement says, when the equilibrium is established according to the reaction, there are 1.4 atmospheres of Br2 left. So that implies that this is an equilibrium amount. Okay, so we're looking for K. We have initial amounts, we have equilibrium amounts. What connects all of those things? Well, we can organize all of this information in an ICE table, sometimes called a Rice table. So we see the table that I have set up for us here below, and that the table has 4 rows: reaction, initial, change, and equilibrium. And here it has 3 columns for each of the 3 components of the reaction. Okay, so in the first row, I will write out the reaction that governs this reaction. So I have 2 NBr3s as my reactant, and then this reaction goes to equilibrium, so there are my arrows, and that becomes 1 equivalent of N2 and 3 equivalents of Br2. Okay. I can then fill in the initial amounts I have for each of these things before the reaction goes to equilibrium. So in the problem statement, I was told that I had 0.6 atmospheres of N2, so I'll put that in there, and 1.7 atmospheres of Br2. So I'll put that in there. The problem statement doesn't say anything about how much NBr3 I have at the beginning of the reaction, and so I can infer, because we talk about having an evacuated reaction vessel, that means I have 0 atmospheres. Okay, so to fill in my change row, I'm going to set the total change in the reaction equal to X. Because this reaction goes to equilibrium and not to completion, I can't use limiting reactant to figure out how much I make. Instead, that's an unknown quantity. So I also have to figure out which direction my reaction is going to go to get to equilibrium. In this case, I see that I have to go from from products toward making reactants, because I don't have any of my reactant NBr3. And so that means that to get to equilibrium, I'm going to make 2 equivalents of NBr3. So I write that as 2 times X. That 2 is the stoichiometric coefficient. That also means that I'm going to lose 1 equivalent of N2, and I'm going to lose 3 equivalents of Br2 as those are transformed into NBr3. To figure out the equilibrium amount, I just add down each column. So my equilibrium amount of NBr3 will be 2 times whatever X is. My equilibrium amount of N2 will be 0.6 minus whatever X is. And my equilibrium amount of Br2 will be 1.7 minus 3 times whatever X is. Okay, so normally I might, or in another type of problem, I might put substitute these values back into the expression for Kp, and then use Kp to solve for x. In this problem, I don't have Kp, so there must be another way to solve for x. Some information that I haven't used yet that might help me is that I know that I have 1.4 atmospheres of Br2 at equilibrium. So now I have an algebraic expression for how much Br2 I have at equilibrium that will allow me to solve for x. And so if I rearrange this, I get that x equals 0.1 atmospheres. Okay, so now since I know what x is, I can use that in the expressions that I have for equilibrium amounts of NBr3 and N2, and I can work out that at equilibrium, I'll have 0.2 atmospheres of NBr3, and I'll have 0.5 atmospheres of N2. And then I already know that I have 1.4 atmospheres of Br2. All right, now I can take these equilibrium amounts and put them back into my equilibrium constant expression. And now I can solve for K. All right, so partial pressure of N2 at equilibrium, we said, is 0.5 atmospheres. I can multiply that by the 1.4 atmospheres of Br2 cubed, divided by the 0.2 atmospheres of NBr3 squared. And then if I do that arithmetic, I'll see that I get 34.3. So that's my value of Kp equals 34.3. Okay, so in this problem, we were asked to find Kp. So we still set up our ICE table in order to organize all the information that we had about initial and equilibrium partial pressures. From there, we could set up this important algebraic expression that let us solve for x, and then we can use what we know about the equilibrium constant expression to solve for k.